Most of the scenarios that we've looked at with probability involve just one single option or one single experiment. When we start looking at experiments connected together, so one after another or multiple choices, the probability becomes a little bit more complex. This type of probability allows us to understand things like games, such as cards. When we talk about multiple choices, there's two situations. Either the event is replaced or it's left out. Replacing the event means that each event does not alter the total number of outcomes because the event does not disappear. So things like removing a marble and putting it back in the bag. I did not change the total number of outcomes. I did not change the total number of events. There's still that marble in the bag. When I roll a die, for example, brainstorm other situations where the total number of outcomes does not change in a probability experiment. In order to find the probability of multiple choices, we need to first find the original probabilities of each event. In this case, we're rolling a die. What's the probability that you'll roll a 4 and then roll another 4? We are replacing the event because when I roll a 4, that does not change the probability of rolling a 4 again. There's still 6 sides on the die. There's still one side that has a 4. So the probability of the first roll, there's 1 in 6. The probability of the second roll, still 1 in 6. We didn't peel the sides off the die. Nothing changed. Still 6 sides, still one side that is 4. Once I have these two probabilities, I'm going to multiply the probabilities together, just like an AND scenario. So AND probability. What's the probability that I roll one or a 4 and then I roll another 4? I multiply them together. 1 times 1 is 1. 6 times 6 is 36. If necessary, simplify. In this case, 1 in 36 is our probability. Let's try this next problem together. You have a bag of toys. There are 4 stuffed animals, 10 bouncy balls, 6 action figures. If you put the toy back each time, what is the probability if you pull out a stuffed animal and then an action figure? So we're putting the toy back. That means when we remove a toy, it does not change the total number of outcomes or specific events in the bag. We start by finding the individual probabilities of pulling out a stuffed animal and pulling out an action figure. If you add up the individual outcomes, 4 stuffed animals, 10 bouncy balls, 6 action figures, you get a total of 20 outcomes, 20 possible toys that could be pulled out of the bag. 4 of those toys are stuffed animals. Out of 20 gives us a 4 in 20 probability. 6 out of those 20 are action figures, so that's a 6 in 20 probability. Multiply those probabilities together. If you'd like to simplify them before, it makes simplifying at the end easier, but it doesn't mean you don't have to simplify. So I'm going to multiply straight through. 4 times 6 is 24. 20 times 20 gives me 400. And I'm going to simplify this. I'm going to use the single mountain method. I'm going to find the factors of the smallest number, and I can use my calculator to do this. So I always start with 1 and 24. 24 divided by 2 gives me 12. 24 divided by 3 gives me 8. 24 divided by 4 gives me 6. Divided by 5, it doesn't give me a whole number, so I'm going to move right over to 6, other side, so I'm done. 400, I would divide each of those factors out. 400 divided by 24, decimal. Divided by 12, decimal. Divided by 8 gives me a whole number, 50. That's how I know it's my greatest common factor. Divide top and bottom by 8. 24 divided by 8 gives me 3. 400 divided by 8 gives me 50. So it's a 3 in 50 probability that I'll pull a stuffed animal and then an action figure, in that order. On your own, try the next problem. When the event is removed, this means that each event alters the total number of outcomes. This is situations where I remove a marble from a bag. That changes the total number of marbles in the bag, so it's the total number of outcomes and even the number of specific events. If I take a blue marble out, for example, I'm changing the blue events. Think of other situations where you might not replace the event. You might remove it from the experiment. In a problem like this, you're going to proceed just like if you had replaced the event. You're going to find the original probability of each event. So the probability in this case, we have a bag of 10 marbles. 3 are blue, 2 are red, 5 are green. What's the probability that you'll pull out a blue and then a green? Well, the probability of pulling a blue marble, there's 3 specific events out of 10 total outcomes. That's 3 out of 10. Now, if I take that first marble out, that blue marble, hypothetically, I'm taking it out, putting it in my pocket, how many total events are there? Well, if I'm looking at green, there's still 5 green events, but there's only 9 total outcomes. There's only 9 total marbles. So it's a 5 in 9 probability. So every time you remove an event, remove 1 from the total outcomes and that specific event. So we only have 5 green, 2 red, and only 2 blue to choose from. If it helps, cross them out and rewrite the numbers as you go. So now I'm going to multiply the probabilities together. 3 times 5 is 15. 10 times 9 is 90. Then I'm going to simplify as always. So I'm going to find the factors of my smallest number. Divide top and bottom by 15. I get 1 in 6. It's a 1 in 6 probability that I'll pull out a blue, then pull out a green. So remember, the only big difference here is that the outcomes and events can change. We're still multiplying. Let's try a problem together. We have the same bag of 10 marbles. 3 blue, 2 red, 5 green. What's the probability that you'll pull out a blue and then another blue? Well, right now there's 3 blue marbles out of 10 total marbles. So it's a 3 in 10 probability that I'll pull out a blue marble. To pull out another marble, we need to look. If I took that marble out, put it in my pocket, it's no longer in that sample space. I have a total of 9 marbles. 5 are green, 2 are red, and only 2 are blue. So the probability of pulling out a second marble, a second blue marble, is now 2 in 9. So I need to multiply those together. 3 times 2 equals 6. 10 times 9 equals 90. I'll simplify by finding the factors of the smallest factor. 90 divided by 6 gives me a whole number, so that means it's my GCF. So I get 1 in 15. There's a 1 in 15 probability I'll pull out 1 blue marble and then pull out another blue marble. On your own, try the next problem, and we'll check it in class tomorrow.